Dynamic systems is how I understand the world and understand how everything works. Originally developed for controlling machinery and physical objects, the same fundamentals in theory and the modeling and the simulation can also be used on all other systems. Also, systems that are not typically a mechanical physical system. And different sorts of physical systems can also be modeled. So we can model, for instance, the virus. If you want a dynamic model for the virus, I can create that for you. I will need assistance from someone who actually knows biology. So if you have a biology expert, I can sit together with this expert and we can create a dynamic model so we can simulate and learn about how the virus works. Also, political and sociology can be modeled into a dynamic system because it's a process that changes, and everything that changes is a dynamic system, and then we can use the same methods, the same theory, to learn about it, to understand how it works, through simulation, and then we can also use methods to develop a control strategy. So we can, for instance, control the economy through the same methods that we use to control a heave-compensated platform, like the one I'm going to show you here now. This is an example of one of the systems I made with simulation of a dynamic system. We have a platform like this on the vessel, and the vessel moves in the waves, the platform moves. That is problematic if you're going to use this, for instance, alongside something stationary, and you want to place something on the vessel, and it moves. That is difficult. It's easy to destroy things. So if you can have a compensation on this platform, so the platform is compensated, so it stays fixed in position. This is a heave-compensated system, and we made this back in the day. You can see it here. Also, for this system, we developed a simulator, the CDP simulator. It's in the top section here. I started the creation of this, and then we got the others put together, and they soon saw exactly how it worked and understood how it worked, so they were quite soon able to both use it and implement additional functionality into this. So that's an excellent tool. The origins of dynamic systems for me, actually it originated before I learned this. I learned about dynamic systems theory from the great professor at the school here in Ålesund, Professor Harald Indestad. And this culminated in the work I did for my thesis. It's the modeling and simulation of the control of the OEV vessel. It's sort of a boat, sort of a hydrofoil. And in here we can find descriptions of the theory of what dynamic systems is. here is the theoretical foundation. This is not anything controversial or unique. It's a description for how to model a dynamic system into a state variable model using differential equations. We can model anything. What is a bit special about this is that already back then I introduced methods for dealing with nonlinear systems, because practical systems, they are nonlinear. And here we also have the principle for simulation of a nonlinear system, which of course the CDP Sim simulator I showed you uses. And what can we find out of this? We have a dynamic system. It could be an economic system, it could be a virus, it can be this platform we want to compensate. We have set up a set of differential equations. Those differential equations are then coupled, so the whole thing interacts and everything depends on everything. And that is the clue to this sort of dynamic model. It is connected in a way, so we can see if we push something down here, we can see how that works on the whole system and how that works on other parameters in the system, variables in the system. For instance, if we have a climate model, we can see if something happens down on the Earth, how will this affect, say, temperature, overall temperature over time. We can see that in a dynamic model. And we can use this to do state estimation, like this. That means if we have a dynamic system, we have modeled it in those equations and put it together into a. The model can be very simple if it's a small system. It can be enormous if it's a large complex system. And there will be variables inside here that we can't measure directly. And then we can use state estimation to be able to find the value of things that we can't measure directly. So that is one thing we can use it for. Here is how we can control things. And here we go into how this vessel is modeled, and of course this is this is something you can find it. You can find it in the available technical literature. Jan Morten Krakeli, he was the other person, participant in this, and together we invented this vessel. It's the vessel in itself. It's hopeless. It's no-go. It will not work. The theories behind it and the modeling and the simulation, that works, but the practical implementation and use of the vessel is it's not feasible. After working a few years and on different things, technology of course, I was so lucky to get an opportunity to get into a job where I was able to do practical projects using everything I had learned about dynamic systems to control mechanical equipment and physical systems. And the first system I did, project I did in this company, the company was called Odim. They delivered winch systems. They now had a new deep sea winch system that required some special control to make it work. This was my first, and the last version of this was also my last project I did for Odim. And when I did the last project, I was already then no longer employed at Odim, so they hired me as a consultant, independent from our company, to do this project. And the first project was very difficult. The last project was very easy. I remember how I worked on this. I never saw the system. It was in Baku. I never went to Baku. So I sat there working with another engineer. We worked together, me showing how this was supposed to be implemented and how it works, and it was not necessary for me to join the Odim team down in Baku, because the system had matured, and the system had one very, very important but seemingly small change to the physical system. And this change to the physical system made the control of the winch so much easier and simpler. So it was actually possible to make it work so that it worked very well and worked much more reliable and was much cheaper to set up and test, and also cheaper to maintain. So why didn't I do it the first time? Were they stupid? Why didn't I tell them how they should do it? Well, you learn as you go, and I didn't see exactly how this system was supposed to be. I didn't see how this system would be very, very difficult to control. When I started doing the modeling for the system and doing simulations and then implementing a control algorithm, I didn't see that this was close to hopeless to do. But we managed to make it work. So then it's okay, isn't it? Well, as long as you can do small changes to the system and make the implementation much cheaper and the operation much more reliable and stable for the purpose it is made to do, and that is to place deep-sea seismic cable onto the sea from a vessel, and then recover the cable afterwards. They don't want to have to deal with a very difficult system. And that is one example that you can use me to improve and change systems, because now I have learned. I know how to approach systems like that, and that is not to go deep into the control algorithm and try to make everything work. If you have the chance to be able to provide input on how the system can be configured and made from a higher level, a higher perspective, then you can provide input so that the whole mechanical, physical system can be perhaps slightly redesigned, so it will work. In many cases, such physical systems, mechanical systems, can be redesigned so that perhaps it's not necessary to do any complex simulations and have a complicated control algorithm to control it. So that was some thoughts about control systems and controlling dynamic systems. If I am able to, I may follow up and give you some more stories and information about dynamic systems.